check. I think it is moving or not. Yes, I think it's not coming. Please, 1 second. So we were discussing this question, and it states that a yo-yo is pulled along a horizontal surface by means of a string without slipping. Depending on the angle at which the string is pulled with respect to the horizontal, the yo-yo may move either towards the puller or away from the puller. Determine the critical angle measured from the horizontal at which the direction of motion changes, that is the angle separating forward as well as the backward motion. Also find the corresponding expression for the translational acceleration of the yo-yo's center of mass and its angular acceleration about the center. So here we are going to find out the angle with respect to horizontal for which it is going to move forward as well as in the reverse direction. That is called as a critical angle in this particular case. So for that, we can just draw an approximate figure. Let me draw a bigger one. And this is our inner, and this is center. We have a surface, and in this case, please remember, I am going to write R1 and R2, but this R1 and R2 are the position vectors. They are not the radius. Okay, they can be represented as the radius, but here we are going to find out the torque, and for the torque we should be knowing the position vectors. Okay, and the force is being applied with respect to the horizontal at angle of theta. So let us suppose this is the point at which the force F is being applied, and it is making angle of theta with the horizontal. And this point of contact, let us suppose its position vector with respect to the center O, we call this as R1. And there is a point of contact, let us call this position vector of this point of contact as our R2. So this R1 and R2 are the position vectors, and let us call this as point as A and point as B. Okay. So R1 is a position vector of point A where the force F is being applied, and B is the point of contact where R2 is position vector. Okay. So we can say that our OA is represented a position vector of R1, and our OB, it is being represented by a position vector, that is our R2. And we can draw this figure, especially the OAB part, on the larger scale also. So we have this is our horizontal, and we have on this we have a point A, and to this we are applying the force F at angle of theta, and we have a center O, and we have assumed that this position vector is our R1, this is center O, and we have let me draw this dotted one, and then we have a surface, and on this surface we have a point of contact which we are called as B, and its position vector is our R2. Therefore, we can say let A and B are being represented by our R, and okay, so this is, we come to the later on again visit this figure again, and we apply, so we can say that let us find out what will be the forces and the torque. Okay, and we can write that the moment of inertia about the center of mass is, let us call this as our C times mr2 square, and for solid cylinder this value of C is equal to over half. So we are going to use this general formula, and later on we can substitute this as our half. So first of all, let's find out what will be our forces as well as the direction. And so first of all, let's calculate the torque about the point, about the contact point. And for that we will be requiring the horizontal component as well as the okay. So first of all, let's find out the position vector of the contact point which we have taken as origin. It's horizontal as well as it's vertical. Okay, so first we are going to find out the position vector from our contact point, that is our B, and in this case we have assumed it as our R. And for R we are going to find out the horizontal component as well as the, because from the figure itself we can see that the point A and with respect to point B there is a horizontal component that is involved and there is a vertical component that is involved. So we are going to find out this horizontal component as well as this vertical component. Okay, and this R1 and R2 once again are the position vectors of A and B. Therefore we can write that the horizontal component will be equal to our R1 cos of theta, okay, because we are interested in this component. Horizontal component will be equal to, and this component will be equal to this component. Okay, and then we come to our vertical component. So vertical component is only this much, so we are going to find out this component, that will be our R1 sine of theta and minus from our R2. Okay, so we get our vertical component will be equal to our R2 minus R1 sine of theta. Okay, so this is our R1 sine of theta and total is our R2. So therefore this component comes as R2 minus R1 sine of theta, and this component is our R1 cos of theta. Okay, and these two are equal. So we got our horizontal as well as vertical component. Therefore we can say that our vector r will be equal to our r1 sine of theta I unit vector plus our r2 minus r1, sorry, r1, one second, sorry, this is our r1 sine of theta, my mistake. This is our r1 sine of theta, and this will be r1 cos of theta because theta will be here. And so we get this as r1 cos of theta, and here will be our r1 cos of theta, and this is our j unit vector. Similarly, we can divide our force F into two components. We are going to have F cos of theta, and we are going to F sine of theta. Therefore, we can write that our force vector, which is our F, will be equal to F cos of theta times I plus F sine of theta times j, and torque is our position vector cross force vector. Therefore, we can say that our torque tau is equal to position vector cross force vector, or we can also say it as our x f of y minus y f of x, and the direction of the torque will be our k unit vector. Okay, we already know our x and y. We substitute them, so we get our torque is equal to our x is our r1 sine of theta. X is our horizontal component, so this is our x and this is our y, and f sine of theta minus we have a y component, and y component is our r2 minus r1 cos of theta, and we have our f cos of theta. Okay, for the time being, this k unit vector we are going to ignore it because that is not required right now. So we just open the bracket, we get this as our r1f sine of theta. This comes minus r2f cos of theta plus r1f, this is square cos square of theta, and we can combine these two terms, r1f sine square and r1f cos square. So we get this as sine square cos square will be our 1, so r1f minus r2f cos of theta, and that is our torque. And we can take f as common, so we get our r1 minus r2 cos of theta. Now this equation r1 minus r2 cos of theta is going to decide whether torque will be positive or it will be negative. Okay. So let us interpret this equation. So we can say the interpretation and we have that if our r1 minus r2 cos of theta is greater than 0, therefore we can say that our torque is equal to positive because our r1 will be greater than r2 cos of theta. And under this condition, we can say that our yo-yo, it rotates the yo-yo away from the puller. Rotates yo-yo away from the puller. This is the first, and then we have a second, which will be reverse of that. That is r1 minus r2 cos of theta is less than 0. Torque will be equal to negative, and if torque is equal to negative, yo-yo towards the puller, towards the puller. Therefore, the critical angle will be when this relationship will be equal to 0. You can say our critical angle is r1 minus r2 cos of theta is equal to 0, and this critical angle, let us call it theta c. Therefore, we can say theta c is equal to cos inverse of r1 by r2. This is our value of the critical angle. And secondly, in the part B, it is asking about the angular relaxation about the point of contact. So we have part B. So we can say that the moment of inertia about the point of contact, moment of inertia, and the point of contact is taken as B. So moment of inertia about B will be equal to that we can also called as moment of inertia about the pivot point, which will be equal to moment of inertia about the center of mass plus, and basically with respect to parallel axis theorem, center of mass, and this is our distance and its square. And we can write that this our I pivot will be equal to, and this I center of mass is our C mr2 square. So we can say this equal to C mr2 square plus mr2 square, which can be written as C plus 1 times mr2 square. And now it is quite simple to solve. It is only calculation is left, and we can also say that if alpha is our angular acceleration, so we can say for angular acceleration is equal to alpha, then this alpha will be equal to torque about and I pivot, and torque we already know, so we get the angular acceleration is equal to torque is our F r1 minus r2 cos of theta, and I pivot is our C plus 1 multiplied by mr2 square. And next is our translational acceleration. Translational acceleration of the yo-yo center. And which is basically we can say no slip constraint. Okay, and for that we can use our basic equation. First is our Newton's law in horizontal direction. So we can say our, if A is the linear acceleration, so we can say our linear acceleration of yo-yo center, if that is our A, therefore we can write the equation that the F cos of theta minus the frictional force is equal to m times A. Okay. And rotational about the center, rotation about center, and we have two forces. One is a frictional force, other one is our applied force, and their distance with respect to the origin is our R2 as well as R1. So rotation about the center will be, we can say, our torque tau, and that will be equal to our moment of inertia about center of mass multiplied by our alpha. And this torque will be the net torque because of both our applied force as well as the frictional force. So we can write this as our Fr2 minus Fr1 is equal to, and this will be equal to ICM multiplied by alpha. And for pure rolling condition, we know that our A, that is linear acceleration, will be equal to alpha times R2. Okay, so this is the condition for our pure rolling. And we can use, okay, let me substitute value of alpha first. So we get this as Fr2 minus Fr1 is equal to ICM, and this comes as A upon R2. And now we can substitute value of friction from here. So we get our friction is equal to F cos of theta minus MA. So we are going to substitute value of friction. We get this as our F cos of theta minus MA times R2 minus F times R1 is equal to ICM, we already know, is our C multiplied by M R2 square, and this comes as A upon R2, and this R2 goes by square, and we open the bracket, and we get from here that our F R2 cos of theta minus MA R2 minus F of R1 is equal to, we have this as CMA R2, and we can take F as common on the left side. So we get this as F is equal, F will be our R2 cos of theta minus R1, and A on the right side. So we get this as our, this will be MA, we can take as common, so this comes as A multiplied by M is equal to C times R2 plus, or we can take R2 also, C plus 1 times R2. So therefore from here we get our acceleration A will be equal to F upon MR2, and we have this as our R2 cos of theta minus R1 divided by C plus 1. Okay. So in this case once again with respect to acceleration, if acceleration is greater than 0, which is positive, same condition. So if acceleration is greater than 0, which means it is positive, so it is going to roll towards the puller, towards. And if our acceleration is less than 0, which is it is means negative, it is moving away from the puller. Okay. And at critical angle, we know that our cos of theta is equal to R1 by R2. So R2 going to cancel out. So critical angle is our cos of theta is equal to R1 upon R2. So if we substitute this equation, we get our, this is R2 multiplied by R1 by R2 minus of R1. So here this R2 cancel out, R1 also, this comes as 0. Therefore at critical angle, the value of acceleration, that is of A, is equal to 0. So we can say there is no net translational acceleration. So we can say no net translational acceleration. And so which basically means that at critical angle, the line of force is going to pass through the straight through the point of contact. Okay. And so the pulling can't rotate the yo-yo at all and only translate. And sometimes it is also called as a zero lever arm. Okay. So we have to remember that. So we can say that therefore we can say our at critical angle, this means that the line of force passes straight through the contact point. Straight through the contact point. So pulling cannot rotate the yo-yo at all. So means the pulling cannot rotate yo-yo at all. So we can say it only translated. We can say only translated. Only translate it. And like I said, this is called as this is our zero lever arm condition. Okay. So this completes all the questions for today about our yo-yo. I think we have covered most of the questions about the yo-yo, and if required we can do another, but I think anyways I'll see to it. If there are any more questions which are based on this yo-yo, we can cover them in the further part also. So this completes all the questions for our yo-yo. And sorry about once again today, there is some internet problem and it gets disconnected. My apologies for that. It is happening quite regularly now, and we'll try to sort it out. Thank you.